5G and fiber, and really getting to the parts of the world that are the hardest to reach, the most difficult to reach, 3%, possibly 5%. And I think it really quite nicely complements and 5G. We've launched and now have active over 1,500 satellites. The combined power of all the satellites is over 5 megawatts. So there's over 5 megawatts of solar from all the satellites combined. They're capable of outputting about 30 terabits per second of data, and starting in actually next month, almost next month, I should say. Starting in August, we should have global connectivity for everywhere except the poles. Now, as I said, it's really meant for sparsely populated regions. So because our spot size, talking in terms of cellular, is quite big. So we're well suited to low to medium density areas, but not to high density areas. In the high density areas, we will be able to serve a limited number of customers. But it is operational. We recently passed the strategically notable number of 69,420 active users. And we're, I think, on our way to having a few 100,000 users, possibly over 500,000 users within 12 months. So I think it's growing rapidly. And we're continuing to innovate the user terminal and the satellite and the ground stations and sort of gateways and points of presence. And then notably for Starlink, relative to, say, other satellite communication systems, we are at around 500 kilometers, whereas the geosynchronous satellites are around 36,000 kilometers. So latency for a Starlink system is similar to latency for ground-based fiber and 5G. So we're expecting to get latency down under 20 milliseconds. So you can still do it feels very fast. Like there's no lag, and you can play, for example, competitive video games on a Starlink system. When I gave a talk a few years ago about Starlink, I was asked for what's my goal for Starlink. And I said, well, our goal is not to go bankrupt. Because as you point out, every other low Earth orbit communications constellation ever done has gone bankrupt. Now, some of them have emerged from bankruptcy, but let's just say the original owners did not benefit from those constellations. So, yeah, they've either gone bankrupt after, most of them went bankrupt before even deploying their constellation fully, and even the ones that did deploy their constellation, they still went bankrupt. So step number one for Starlink is don't go bankrupt. That is, and then if we succeed in not going bankrupt, then that'll be great, and we can move on from there. But I do think from a technology standpoint, Starlink is quite different from prior LEO constellations in that the technology that we're deploying is very advanced. What happens often with space-based technology, somewhat ironically, is that it tends to be older technology that exists on the ground. So companies generally have been very conservative, so they've said, well, we want technology that's proven to work on the ground, and then we have to test it for years to make sure it's going to work in the vacuum of space with a higher radiation load and that kind of thing. And so the technology that's generally been launched into orbit has been older technology. And we took the opposite approach and said, we're going to make technology that is, in some ways at least, more advanced than what is on the ground. And we're just going to take a chance. And And so we have what's probably fair to say are the most sophisticated, the most advanced phased array technologies that, to the best of knowledge, no one has. It's not even at sort of military level. It has this level of sophistication with phased array technology. That's sort of quite important for a fast-moving LEO constellation, because the terminal, which is a user terminal that is also phased array, and the terminal on the terminal on the satellite, the antenna on the satellite, they're both phased array. So you can switch from one satellite that's moving rapidly overhead to another one, and do so at the microsecond level. So there's no, you can't tell as the system is switching over from one satellite to another. There's no change in latency or jitter from one satellite to another. And a single satellite can illuminate many different user cell spots on the ground. And it's a digital phased array system. So we can continue to program and reprogram the system to greater efficiency because it is digital. So, like I said, to the best of my knowledge, it is the most advanced phased array system in the world. So that's pretty cool. We also have the advantage of a launch system that is capable of a very high launch rate and capable of putting a lot of mass to orbit. I believe last year, SpaceX delivered about 2/3 of all payload to orbit. And this year, we may deliver closer to 80% of all payload to orbit of Earth. Mm-hmm. Just to put that in position, so, and of the remaining, of course, it remains to be seen for this year if we actually put close to 80% of all payload to orbit. But of the remaining, let's say roughly 20%, about 12% would be China or thereabouts, and then 8% is everyone else. So the sheer mass to orbit capability of the Falcon 9 rocket is, because it is a reusable booster and the fairing is reusable, so we only have to make the upper stage, that has never existed before, and the cost of mass to orbit also is the lowest it has ever been. So because of reusability, so this is the two work together quite well. But it has been quite an adventure learning how to make these advanced satellites and learning how to make so many of them, and the user terminal and the gateway. And the satellites, for example, use a SpaceX-developed Krypton Hall effect thruster, which basically shoots out high-speed ions of Krypton. It's kind of cool. Superman, watch out for our satellites. Don't go close to them. So like Krypton. Getting close to launching satellite 1.5, which has laser inter-satellite links. And that'll be used especially for continuous connectivity over the Arctic and Antarctic regions, or basically the high polar regions, the high latitude regions. And then next year we'll start launching version 2 of our satellite, which will be significantly more capable. And then all satellites from 1.5 onwards will have inter-satellite links. And then we'll start getting our gateways and our points of presence to really directly to the major server centers. So the data really goes directly from user terminal directly to the server center. So if somebody's using YouTube or Netflix or Google search or Xbox, whatever the case may be, Amazon Web Services, the data flows in the shortest path possible, thus minimizing latency and jitter. So even if big chunks of the internet go down, then you still have connectivity. So I'm pretty excited about the future. It's looking, we're getting overconfident, but it's looking quite positive. And like I said, it serves as a great natural complement to major telco, fiber, and 5G. So right now we're basically, it's like $500 to order a dish, and it's about the same. It's the same price everywhere in the world. The only thing that changes from one country to the next is our taxes and import duties. So it's the same price everywhere in the world. We're taking into account sort of exchange rates and import duties and transport and stuff like that. So, and then it's $100 a month. I mean, to be totally frank, we are losing money on that terminal right now. That terminal costs us more than $1,000. So we obviously are subsidizing the cost of the terminal. Now we are working on sort of next generation terminals that provide the same level of capability, roughly the same level of capability, but costs a lot less. So that's one area of development for us. Because obviously selling terminals for half price is not super compelling at scale. In order to do millions of that, that's tricky. And over time, we would like to reduce the terminal cost from $500 to, I don't know, $300 or $250 or something like that. We do make it very easy to install. So because we knew that our customers would be all over the world, often in very remote regions. SpaceX was really started with the goal of trying to make life multiplanetary, or making as much progress as possible towards making life multiplanetary. In order to make life multiplanetary and become a spacefaring civilization, in the truest sense of the word, the rocket technology must be improved dramatically. In particular, the holy grail for rocketry is rapidly reusable, reliable rockets. RRRR. Like a pirate. With Falcon 9, we've achieved, I think, the most efficient reusability of any rocket to date. We've got boosters now that have flown 10 times, and some that are slated to fly 20 or possibly 30 times. So this is a lot of reuse that we're getting. We're also now getting quite good at catching the nose cone or fairing. And so when you look at the cost of the rocket, you've got about 60% of the cost, depending how you count it, about 60% of the cost in the first stage, and about 10% in the fairing. So that means we're recovering about 70% of the cost of the rocket. And then you've got about 20% of the cost in the upper stage, which is lost every time, about 10% of the cost in the launch itself and the recovery and refurbishment process. So this is really a very good number for a rocket, but we still need to take this to another level. That's why we have the Starship development, which is a much bigger rocket. It's the biggest rocket ever developed. It will have more than twice the thrust of the Saturn V moon rocket, and it's designed for full and rapid reusability. So this is with a 100-ton to orbit capability, possibly with further refinements, 150 tons to orbit. And moreover, it uses lower cost propellant. So it's a 3.5 to 1 mass ratio of oxygen to fuel, and the fuel is liquid methane, which is the lowest cost fuel in the world. And the pressurant is autogenous oxygen and methane gas instead of helium with Falcon 9. So Falcon 9 uses helium. It uses rocket propellant grade jet fuel essentially, which is actually quite expensive, and helium for pressure, which is quite expensive. So the cost of propellant for Starship, even though it is much bigger, will be really comparable to the cost of propellant for Falcon 9, but it will have full and rapid reusability. So the crazy thing is that if things go according to plan, we'll have a rocket with 100 ton to orbit capability that has a marginal cost per launch of around $2 million, which is less than our little Falcon 1 rocket that we started out with. When you add in orbital refilling, which really means that 2 Starships need to dock on orbit, one transferring propellant to the other, sort of like aircraft aerial refueling, but this is orbital refilling, primarily of oxygen. Then you can deliver over 100 tons to the surface of the Moon or Mars, possibly 200 tons. So Starship is the first system that will be capable of building a base on the Moon and a city on Mars. So we're hoping to do our first orbital launch attempt in the next few months, and we'll certainly will have a booster and a ship, an orbital capable booster and an orbital capable ship, and the orbital launch site will